Muscle is the primary means of producing movement for living systems, and being able to move is critical for finding food and other resources and for finding mates. Without muscles, none of that would be possible, so muscles are critical for almost all types of behaviors. Muscles don't behave like typical man-made actuators like motors that are used in robotics applications. A motor can begin generating full torque almost instantly. It can also generate that torque regardless of the position of the limb or the load it's trying to move. And motors can generate negative torques just as easily as positive ones. Muscles are quite different. They have springs and dampers, which mean that they can only generate forces slowly compared to motors. The amount of force they can generate also depends on the current length of the muscle. A muscle that's stretched will generate less force for the same stimulus than one that's at its resting length. This means that the amount of force the muscle generates will change depending on the angle of the joint. Finally, muscles can only pull. They can never produce pushing forces. This means that muscles must work in antagonistic pairs to produce a full range of movement. For example, your bicep muscle works to flex your arm, while your tricep muscle works against the bicep to extend your arm. There are two different types of models that are typically used to simulate the behavior of muscle. The first of these is the Hill model. It's a purely mechanical model built from the systems engineering perspective. The early pioneers in the field of muscle mechanics knew almost nothing about the internal structure and functioning of the muscle, so they had to treat it as a black box and attempt to map the input-output characteristics of muscle in an effort to formulate a mathematical model that could predict its overall behavior. The second type of muscle model was formulated once the sliding filament theory was proposed by Huxley. It was built using a reductionist approach that takes into account the actual molecular structure of the muscle. Muscles work using a ratcheting mechanism between actin and myosin molecules within the segments of the muscle. This type of model attempts to predict the developed tension by simulating the forces produced by the cross-bridge attachments between actin and myosin molecules. AnimatLab uses a simpler Hill-type model. It provides a reasonable approximation of the behavior of the muscle while being much simpler to implement and to use. It also runs faster, which allows you to simulate numerous muscles simultaneously. However, you need to keep in mind that this model only simulates the overall behavior of the muscle. It doesn't represent what's actually happening within the muscle at the molecular level, and muscles don't really have the actual parts that are shown in this model. The Hill model used in AnimatLab is shown here. It's composed of two sections, a serial elastic and a parallel elastic component. The serial elastic section has one spring with a spring constant, KSE, that determines the stiffness of that spring. The other section has another spring that's in parallel with a viscous damper and an active force generator. All muscles resist changing their length. The damper models this by adding a resistive force that's proportional to the velocity of the muscle. All of the parts mentioned so far make up the passive properties of the muscle, but muscles can also actively generate tension. To do this, an active force generator is in parallel with the damper. When stimulated, it applies a compression force that pulls on the serial part of the muscle. The amount of tension actually applied by the muscle depends on the values of the two spring constants. There are also three primary relationships that are important to emulate the behavior of muscle. These are the tension length, force velocity, and stimulus tension curves. As I mentioned earlier, the amount of force a muscle can generate is dependent on the length of the muscle. AnimatLab uses an inverted quadratic function to model the tension length curve. This curve determines the percentage of active tension that's actually applied at a given muscle length. Hill also discovered that the viscosity of the muscle is not actually linear. He derived a nonlinear equation to describe this relationship. However, AnimatLab uses a simpler linear damping coefficient instead. This simplifies the muscle model and still provides a reasonably accurate simulation of the behavior of a muscle. The third of these relationships is the stimulus tension curve. This sigmoidal function relates the input stimulus strength to the active tension that will be applied in the force generator. In this tutorial, we'll perform a virtual experiment that you can use on real muscles to determine their spring constants and damping coefficients. We will add a muscle and set the parameters. Then we'll try and determine what those values are experimentally. Let's begin by opening the existing spring project. That project has a test rig that we'll use to perform our experiments. You can find the spring tutorial at C, Program Files, AnimatLab, Tutorials, Body Parts, Spring. Once it's loaded, select the Save Project As item from the menu and rename it Muscle. The current test rig is way too big for a muscle, so we need to shrink it down to size. Select the root part and change its length to 0.5 meters and its width to 1.1 meters. Then select the arm and set its size to be 0.5, 0.5, and 0.1 meters. Change its Y location to be 0.3 meters. Select the left side and set its height and length to be 0.5 meters. Change its local X to be negative 0.5 meters and local Y to be 0.3 meters. Select the right side and set its height and length to be 0.5 meters. Change its local X to be 0.5 meters and local Y to be 0.3 meters. Next, we need to disable all the spring stuff from the previous tutorial. Make sure the spring is disabled. Then disable the spring adapter and the spring stimulus. Next, let's add a muscle to the arm. Select the linear heel muscle as the default body part type and add it. Change its name to be muscle. We'll be setting the spring constants and damping coefficient to specific values for now. And then I'll show you how to try and experimentally determine what those values are. Set KSE to 500 Newton per meter, KPE to 125 Newton per meter, and B to 100 Newton seconds per meter. Next, we need to string the muscle between attachments. This is what specifies how the muscle actually connects to the body. In the earlier spring tutorial, we added attachment points to the side and body of the test rig. We'll use those attachments to define where the muscle will be located. The contractile forces that the muscle produces are applied to the body at these attachment points. You're not limited to only using 2 attachments. Sometimes muscles can wrap around bones or other parts of the body, and this can have a profound impact on the behavior of the muscle by changing the angle of attack and thus the vector that force is applied to the body. You can simulate this in AnimatLab by stringing the muscle using multiple attachment points. Force is always applied from one attachment point towards the next closest point to ensure that the force is applied in the correct direction. When you click on the muscle attachment property, it opens a dialog with a drop-down that lists all attachments in this body. Select the one you want and then hit the Add button. Add the attachments in the order that you want them connected. You can change the order by using the up and down arrows that are to the right. Add the left attachment and then the arm attachment. When you first define the attachments for a muscle, it calculates the muscle length and sets this value as the resting length of the muscle. The resting length centers the tension length curve, while L width determines how spread out the curve is. Set L width to be 10 centimeters. Now we can see that at the resting length of 0.5 meters, 100% of the active tension is applied to the muscle. As we move away from that length, a smaller percentage of the active tension will be used. 5 centimeters away, only around 75% of that tension will be used. Next, we need to set the stimulus tension properties. This is a sigmoidal curve that relates an input muscle membrane voltage to an active tension. In AnimatLab, you use a non-spiking neuron to emulate the properties of the membrane voltage of the muscle. Spiking motor neurons stimulate the muscle, and those signals are integrated and used to drive the active force generator that produces muscle contraction. The amplitude determines the maximum active tension the force generator can apply. Set this value to be 1 kilonewton. Steepness determines how rapidly the sigmoid rises. Increasing this value increases the steepness. Set this to be 150. The X offset determines where the center of the curve is located. In this instance, a muscle membrane voltage of negative 40 millivolts produces half of the maximum active tension. The gain limits lets you define the limits for your input and output variables. If the voltage goes below the lower limit, then the lower output value is used, regardless of the value from the equation. Set the upper output value to 1 kilonewton. So how do you interface the neural network to the virtual muscle to produce contractions? You do this using a muscle node in the behavioral editor. Add one of these items and then go to its muscle ID property. This will list all of the muscles of the body. Choose the one that you want and select it. Now, when you draw connections to this node, you'll be supplying inputs and outputs to the chosen muscle. If you forget to choose a muscle ID, then even though your neural network may be doing stuff, it will not have any effect on the muscles because you haven't told it which one to interface with. Change its name to muscle and select muscle as the ID. Now add a non-spiking neuron. This will function as the membrane of our muscle. Change its name to MV for muscle voltage. Set its resting potential to -100 mV and its time constant to 70 milliseconds. The time constant will control how the action potentials for motor neurons are summed up. If this value is too small, then the effect from a motor neuron spike will totally dissipate before a new spike arrives. Increasing this value gives the muscle more time to sum the spikes and use that to produce tension. Draw a connection from the neuron to the muscle node. This adds an adapter between them. However, most of the time when you're connecting muscles, you'll just use the default adapter settings. The stimulus tension curve is the primary means of controlling how the voltage affects the contraction of the muscle. For these experiments, we need the muscle to be held steady, and then we'll stretch it by 1 centimeter, hold it, and then relax it back to its resting length. So let's enable the motor on the prismatic joint. Then add a motor velocity stimulus. Call it stretch. Set its end time to 5.025 seconds, start time to 5 seconds, and velocity to -40 centimeters per second. This will ensure that the muscle will be stretched by 1 centimeter. Now add a new chart and add items to view the membrane voltage of the neuron and the tension and active tension and length of the muscle. Run the simulation. At 5 seconds, the muscle is stretched. This causes a spike in the muscle tension because the PE segment of the muscle is damped and cannot react quickly to changes in length. This means that the SE segment must take up the brunt of the length change, and this causes an increase in the tension. But the PE segment slowly adapts to the new length until an equilibrium is reached with the new steady state tension. Now let's add a new motor velocity stimulus to relax the muscle. Name it Relax, set its end time to be 8.025 seconds, start time to be 8 seconds, and velocity as 40 centimeters per second. Run the simulation again. Now at 8 seconds the tension drops back down to 0. However, to get a better idea of what's happening, it would be helpful if we had some base level of tension and then stretch the muscle. Let's produce 10 newtons of force. To do this, go to the calc stim property of the muscle. This dialog lets you calculate the voltage stimulus you'll need to produce a desired tension in the muscle as it's currently configured. The calculation shows that we need a voltage of negative 69.13 millivolt. Our non-spiking neuron has a default conductance of 1 microsiemens. With a resting voltage of negative 100 millivolts, this is a change of 30.87 millivolts. So we need to add a tonic current stimulus to the neuron of 30.87 nanoamps. Set it to run for 20 seconds. We can use the response of the muscle to this small, rapid stretch to estimate the major muscle parameters. Let's view the muscle data and collect some of the important data points. Just before the stretch at 4.99 seconds, the tension is 9.996 newtons, and the length is essentially 0.5 meters. Now we need to find the peak tension. Let's look for where the tension is going up and then going back down. At a time of 5.026 seconds, the tension reaches a peak of 14.701 newtons, and the length is 0.51 meters. Now let's look for where it reaches steady state again. Go to 7 seconds and the tension is 10.863 newtons. So how can we use this to estimate muscle parameters? When the simulation starts, we begin stimulating the muscle and it begins to generate tension, but its length is held constant. This is an isometric contraction. Then at 5 seconds we rapidly stretch the muscle. The PE portion cannot respond quickly because of the damping, but the SE portion can. This causes a spike in the tension. Then the PE segment slowly adapts to the new muscle length till it reaches a new equilibrium resting tension at this new length. Most of the tension in the initial rapid stretch occurs because the SE spring is stretched. This gives us a change in tension for a change in length, and we can use this to calculate the stiffness of the SE spring. When we do this, we get a value of 470.5 newtons. This is different than the actual value that we used of 500. So why is this? Try and think about what could cause this error, and we'll come back to this in just a few minutes. Next, after the peak tension is decayed back to a new resting level, the tension is greater than it was before. This is due to the passive properties of the muscles. We can again use this change in tension for a change in length to estimate the PE spring stiffness using the equation shown. We get a value of 106.6 newtons per meter. Again, this is different than the actual value that we used, which was 125. So what caused this? Part of the reason is that we're using the SE estimate that we calculated earlier, and we know it's not quite correct. More importantly though, is the effect of the tension length curve. We've stretched our muscle, so the active tension that's applied at this increased length has decreased, and this affects the new equilibrium position. If you were to increase the L width parameter so that it's very large and the tension length relationship disappears, and if you use the real value of KSE, then you are able to get the actual value for KPE here. Finally, how do we estimate the damping coefficient? When the muscle is stretched, it takes some time to decay back to a new resting tension. We can use this to find the time constant of this decay, and that can be used to calculate the damping coefficient. We end up with an estimated damping of 101.5 newton seconds per meter, which is quite close to the actual value we used of 100. So, have you figured out why the KSE value that we estimated wasn't the exact value that we specified? The reason this happened is that we're not able to instantaneously change the length of the muscle. It takes 25 milliseconds to move the muscle to the new position. This gives the PE portion of the muscle a chance to begin adapting to the new length. We can see this more clearly if we set the damping to an absurdly large value. The damping will be so high that the PE portion of the muscle will not have a chance to move much at all. Set the damping to 3000 and run the simulation again. This time the tension at the start of the stretch is 6.36 newtons, and the peak tension is 11.36 newtons. This is a change of 5 newtons for a length change of 1 centimeter. This equals our KSE value of 500 newtons per meter. Set the damping coefficient back to 100. Next, we need to demonstrate how spiking motor neurons can control contraction of the muscle. Disable the stimulus to the MV neuron and then add a new spiking neuron and call it MN for motor neuron. Set its after hyperbolarization time constant to 90 milliseconds and its initial threshold to negative 59 millivolts. This will allow this neuron to generate a low firing frequency for even very small depolarizing current. Connect MN to MV using a nicotinic acetylcholine synapse. Add a new axis to the chart and view the firing frequency of our MN neuron. Then add a tonic current to MN. Call it MN stem. Set its end time to 20 seconds and current to 1.5 nanoamps. Actually, I kind of messed up with the chart. We need to see the membrane voltage of the MN neuron, not its firing frequency. Run the simulation. We cannot see much with the MN and MV on the same axis, so let's split them out into separate axes so we can see them better. Now we can see that each spike of the motor neuron produces a twitch voltage in our muscle membrane. However, we still have a problem in that we're not really getting a twitch in the muscle tension. Instead, the tension is jumping up to a base level. The problem here is that the stimulus tension curve still maintains a tension level even very close to the negative 100 millivolt resting potential. So we need to make sure that it goes down to 0 when it gets close. Go back to the stimulus tension curve and set the y offset to negative 13 centinewtons. This will ensure that as the membrane voltage gets near the resting potential, the active tension will be 0. Before we run the simulation, let's move the active tension off onto a separate axis so we can see them more clearly. Now when we run the simulation, we get a nice muscle twitch for each action potential. We can control the dynamics of the twitch by adjusting the stimulus tension curve and the time constant of mv. Now let's see what happens when we increase the current stimulus. Change it to 7 nanoamps. This produces a motor neuron frequency of 10 Hz. This time the twitches overlap and begin adding to produce force. Let's up the current again to 16 nanoamps. This produces a frequency of 20 Hz in Mn. This tutorial has explained the muscle model used in AnimatLab and has shown you what each of the parameters do and how to produce contractions using neural control.